From a cosmic distance, a spiral galaxy appears perfectly static. We see a vast, glowing core and grand arms of light in an unchanging void. But that image hides a massive structural problem. To keep shining, a galaxy has to forge new stars, and it does that by constantly consuming its finite reserves of hydrogen and helium gas. Without a way to cycle material back into the system, the gas eventually runs out. Star formation stops, the lights go out, and the galaxy dies. For a galaxy to survive its own consumption, it needs a continuous, large-scale recycling engine. Astronomers originally assumed that the violent deaths of massive stars would work against this recycling. They modeled supernovae as destructive blasts that would simply empty a galaxy by blowing its gas into deep space. We now know the reality is more complex. These explosive events provide the regulatory heartbeat required to keep a spiral galaxy active. To see how that works, we have to track the expanding shockwave of a single dying star as it reshapes the entire cosmic ecosystem. It begins inside a star at least 8 times the mass of our Sun. For millions of years, the star survives, fusing heavier elements. Eventually, the star reaches the iron threshold. Once the core fuses into iron, it can no longer extract energy. The outward pressure fails, and the internal engine stops. Gravity immediately overwhelms the core, causing the massive outer layers to collapse inward at high speeds. Those layers rebound off the ultra-dense core, triggering a massive burst of kinetic energy that shreds the star apart. This explosion scatters the star's nucleosynthetic ash, heavy metals like iron and oxygen, directly into the surrounding galaxy. The resulting blast wave races into the interstellar medium, carving out massive cavities in the surrounding gas. Our own solar system currently sits inside one of these voids, known as the local bubble. As the wave moves, it clears the neighborhood of small cometary bodies and dust, effectively reshaping the local environment. When this fast-moving wave collides with a dense, dark gas cloud, the extreme pressure instantly compresses the material. This localized compression forces the birth of new stellar nurseries, ensuring a new generation of stars can form from the wreckage of the old. Because massive stars form in clusters and have short lifespans, they often die in a rapid sequence. Their overlapping shockwaves merge together, carving out a massive superbubble within the galactic disk. This diagram shows what happens when a superbubble breaches the edge of the disk. It blows out, launching fragmented gas vertically into the galactic halo. Eventually, gravity pulls these cold gas fragments back down toward the disk, forming what astronomers call a galactic fountain. This fountain is the macro-circulatory system of the galaxy, returning expelled matter to active star-forming regions. These fountains serve as the delivery system for the heavy metals forged deep within the stellar cores. This Milky Way map identifies where the gas falls. The clouds tend to orbit and drop back within 1 kiloparsec of their launch point. Because the fall is localized, the fountains don't erase the large-scale chemical differences across the galaxy. Instead, the time spent orbiting in the halo creates a delay in the mixing of metals, regulating the overall pace of galactic evolution. At the cosmic scale, a galaxy's survival depends on whether its gravity is strong enough to control these internal explosions. This plot for a Milky Way-sized galaxy shows a stable system. The galaxy possesses enough mass to retain and recycle its fountain gas over billions of years. This threshold graph shows a different outcome for dwarf galaxies. When the luminosity of supernovae is too high relative to the galaxy's mass, the system enters the blow-away region. In a blow-away, gas accelerates beyond escape velocity and is permanently ejected into intergalactic space. Without that gas, future star formation is quenched, leaving the dwarf galaxy dead. We can still see the evidence of this violent history millions of years later. By using X-ray spectroscopy to look at the gas trapped between galaxies, we can measure the specific abundances of heavy metals. These metal deposits serve as an archaeological record, containing the integrated history of star formation across the entire cluster. Every detail of a galaxy, its shape, its chemical richness, and its ultimate lifespan, is sculpted by the explosive remains of stars that died eons ago.